In this video, we'll continue the last example about liberals versus conservative. We ended up computing p in the first video of this sequence. Then last video, we computed p to the n, which is the nth power of this using diagonalization, and we got this matrix. So now what we're going to do is we're going to use that formula for p to the n to study long-term behavior of voters. So I want to compute the limit as n goes to infinity of this matrix. Well, once I have the formula, that's not too hard. So Q is going to be the limit of p to the n, which is the limit of 1 over 5, 2 plus 3, 0.75 to the n, 2 minus 2, 0.75 to the n, 3 minus 3, 0.75 to the n, 3 plus 2, 0.75 to the n. Now when the limit of n goes to infinity, the 1 over 5 will stay, 2 will stay. As 0.75 is less than 1, so if I raise it to really high power, it will go to 0. So plus 3 times 0, 3 minus 3 times 0, 2 minus 2 times 0, 3 plus 2 times 0, and so I end up getting 2, 2, 3, 3. That's the limit as n goes to infinity of p of n. Now I want to figure out what happens when I apply this matrix to any state vector. So f, find Q of x0 for any x0. So this is a state vector. So let me say it just to make it clear. Any state vector x0. So it's a state vector. That means the sum of its component is 1. So say x0 is AB, where A plus B is 1. Since it's a probability vector, the total sum should be 1. It's 100% probability. I'm going to apply Q to it. That's 1 over 5, 2, 2, 2, 3, 3. AB, I'm going to get 2A plus 2B, 3A plus 3B, and now let me factor out 2 and 3 from each of the entries. Since we have a state vector, the sum is 1, and so I end up with 2 on 5, 3 on 5. Now, what does that mean for our example? The fact that we are starting with any state vector means that whatever the voter is voting today, as n goes to infinity, that means really, really far in the future, this voter will be liberal in, well, that's 0.4, this is 0.6. So in 40% of the cases, they'll be liberal down the line. In 60% of the cases, they'll be conservative. So So however a voter votes today, for n big, large enough, the voter will end up being liberal 40% of the, with probability 40% or 40% of the election, however you want to phrase it, will be liberal 40%. So let's write with probability 40%, and will be conservative. With probability 60%. Alright, so let's call this vector the 40-60 vector. Let's give it a name. Let's call it Q. There's something special about this. Q has a special relationship with the P we started with, and that's what we want to check out in part G of this problem. So it was 0.4, 0.6. I want to check what happens when I apply P to it. I don't remember what P was exactly, so let's double check. P was 8515, so 0.85, 0.15, 0.1, 0.9. So I'm going to take that matrix and I'm going to multiply it by 0.4, 0.6. So what I'll get is 0.85 times 0.6 plus times 0.4, 0.1 times 0.6, and then in the bottom 0.15, 0.4 plus 0.9 times 0.6. So I'm getting, that's 0.34 plus 0.06. Zero point 0.06 plus 0.54. So if I add it up, I'm getting Q again. In the next video, we'll be looking at what Q is for this matrix. We'll have a definition that will apply to almost all Markov chains, all regular Markov chains. And we'll have a theorem that tells us exactly when it exists, when it doesn't, and stuff like that. We're going to go with something like this, that we get Q back when we multiply P by Q.